Okay, let's see. Is okay. I guess you can see this.
Yes. Can you just
Yes.
change the slide? Yeah, slide is also changing. Yeah.
Okay. So that seems to be working. I'm audible, right?
Yes, yes, you're audible.
Yeah. So the participation numbers are still reasonable, or people are
Yeah,
getting
now I think it
saturated?
is around 45.
Mm. I think
So you
overall
can
people.
start, no? Should we start?
Yeah.
Okay. So welcome to our last talk for today. So let me introduce our speaker, Dr. Anil Shaji. So Anil did his PhD from University of Texas with late Professor E.C.D. Sudarshan, and then he did his postdoctoral study from University of New Mexico. So he joined Isaac Sivandam in 2009 as assistant professor, and presently he is a professor in Department of Physics and also Dean Academics at Isaac TBM. So Anil's research interest is mainly in open quantum system. Apart from that, he is also interested in fundamental aspects of quantum theory, quantum genome effect, quantum information theory, precision, measurement precision, and quantum methodology. So incidentally, Anil, since I and my research interest is also similar to Anil's research interest, I know that some of Anil's work is really pioneering, and he has more than 50 publications in several reputed journals. And during his BSc as well as MSc, he was the gold medalist in his institute, and BSc is done from uh, uh, University College Trivandrum and MSc from IIT Chennai. And he is also member of American Physical Society, and he is reviewer of several internationally reputed journals. And today, Anil will talk about quantum mechanics in daily life, advent of quantum technology. Anil, please, yeah.
Yeah. So, yeah, I had put a slightly different title here, but that was kind of intentional. But it's really the same thing. Thank you, Manik, very much for the kind introduction, and thank you to Dr. Indulekha and all other organizers from the Academy Resonance for providing this forum to reach out to undergraduate students around the country. Okay, uh, I will start probably with I guess, an advertisement for uh, Samsung, I guess. Recently, this thing showed up, maybe a few months back, couple of months back, wherein they are advertising a cell phone, saying that there is something quantum mechanical in its working, and it is secured in its communication by Swiss Quantum. So this is just to bring home the fact that what we called what we call as quantum technologies, uh, which were considered to be rather esoteric maybe few years back, are now in some form or the other. Whether you accept it as real quantum technology or something of a gimmick doesn't matter. They are slowly percolating into day-to-day life in ways that we see and in ways that we don't see. So, as young undergraduates, which is the target audience of this talk, it is important to be aware that maybe a select or high value part of the job market when you graduate and start your careers may require some expertise or knowledge or at least awareness on about quantum mechanics. So I guess you could imagine what would happen when you try to take this cell phone to repair in your local hole in the wall repair shop where some kid is fixes your phone for you for cheap rather than taking it to Samsung's service center. That fellow, I guess, should have at least a working awareness of what the quantumness in the cell phone is, right? So that would be a motivation for talking about quantum technologies. But this is my a way of talking about quantum mechanics first. And this picture about the people going to see the elephant, I often repeat just to bring home the point that quantum mechanics deals with phenomena that are far away from your day-to-day experience. Therefore, very often one makes the mistake of viewing quantum phenomena through the lens of your daily experience and get into knots yourself in terms of your thoughts and getting yourself confused. See what to come back to this parable, what happened here is that the one person thought that elephant is like a rope, the other thought it's like a sphere, one person thought it's like a wall. But I guess the take home message for me from those things is the fact that these guys, these blind people, had previous experience with ropes and walls and spears, and therefore they concluded that the elephant is like that. So the same mistake one should try to avoid when it comes to quantum mechanics, because with your experience with respect to the classical world, you should not end up jumping to conclusions and basically be reluctant to see the world as it is, as described by quantum mechanics, because it is supported by over 100 years of experimental evidence. Okay. So, what distinguishes classical mechanics from quantum mechanics? We will be touching on this on quite a bit along the way in this talk, because we are talking about what is essentially quantum in a quantum technology and what all you can do and what all you cannot do when you talk about quantum technology. So, it is always in relation to what is allowed in classical physics, that you talk about advances or advantages of quantum technologies, because it's always in relation to what is already allowed in classical mechanics. So describing classical systems is something familiar to you. These are the kind of the list of things I have written here are the kind of things that you use, the variables or the descriptors you use to describe a classical system, starting from position, velocity, mass, size, and of course you can go on color and surface texture and whatnot. You can add, and I deliberately put two things here, a football and a wave, because both are classical phenomena, but with very distinct characteristics. And in a sense, quantum mechanics borrows from both when you start thinking about particles in the of very small size and time scales. So of course, these are the familiar variables of classical mechanics, and dynamics is given by Newton's equation F equal to ma. That's about classical systems. One other thing that you learn in your 12th standard electromagnetism or electricity and magnetism chapters is about ammeters and voltmeters. When you talk about it, you always are drilled into this statement that says ammeters have low resistance, voltmeters has high resistance. But if you think about it, what it is really saying is that classical physics allows you to measure a quantity without actually disturbing the value of that quantity. So it allows that idealization wherein the ammeter really has zero resistance. Therefore, it does not alter the current, or it does not affect the current in the circuit if you connect up a ammeter in series to the circuit. If it has an internal resistance, it's going to alter the current. Therefore, it disturbs what you're trying to measure. But classical physics in principle allows you this idealization that tells you that in an ideal world, you can measure have an ammeter with zero resistance, which does not uh, disturb the current in the circuit, or a voltmeter that does not change the voltage at all with infinite resistance. So it allows for that idealization, but it turns out quantum mechanics or quantum particles fundamentally are different in the sense that you cannot do an observation without necessarily creating a disturbance to the system. So this is a caricature of what's called the Heisenberg gamma ray microscope, which is a heuristic way, I wouldn't say a very accurate way, but a heuristic way of understanding that if you try to look carefully at something very, very small, you kind of have to put in a lot of energy in this case to actually see it because it's so small. And in the process of shooting a gamma ray photon onto an electron to see where it is, you are going to disturb the position of the electron so much that or rather, you will make it move so fast that you'll have no knowledge of its velocity or momentum at the time of detecting its position. You may know where it is, but you have now imparted a lot of momentum to the electron, so you don't know what its momentum is, which is again sort of captured in this uncertainty relation that everybody knows regarding a position and momentum. The reason I'm saying this is that already we see there is a crucial difference between what you can or cannot use to describe quantum systems as opposed to classical systems. Because in my previous slide, I had talked about classical variables like position, velocity, and so on. And it's assumed that for any given particle, you can give the values of its position, velocity, momentum, energy, all that without any or simultaneously without any problem. But uncertainty principle tells you that, for example, position and momentum are mutually conjugate variables whose values you cannot specify with arbitrary precision at a time. So what this led to historically, and on the basis of a lot of experiments, is the realization which was codified by von Neumann into the statement that in the end, your best known description of a quantum system is in terms of this abstract quantity called a state vector. Now just think of the state vector, or in this case, what I have shown here is sometimes referred to as a ket vector. If you don't know what it is and what its properties are, don't worry, just think of it as a little container that contains all the information that you can possibly have or you are allowed to have about the quantum system. Okay, so when you actually write it down sometime, and again, I'm putting the spectrum here just to emphasize the fact that the statement that quantum states are associated with this abstract quantity called a state vector, which or a ket vector, which technically is a vector in a complex vector space called Hilbert space. Now, those technicalities are not all that important, but this statement is a codification of experimental result. So in a sense, it's or not in a sense, it is one of the postulates or axioms of quantum mechanics. So to the extent that experiments verify that it's true, it is true. Experiments, if they show that it's not correct in some limit, then you have to say that, okay, this axiom has its limits. It cannot be applied willy-nilly. So what I've written here is a complicated expression that that is meant to tell you that yes, when you write down the state vector on a piece of paper, you may put many pieces of information in it depending on what you want to do. On the rightmost side, I have a function which is essentially a Gaussian function, which is sort of representing the fact that this is what you know about the position of the particle. There are some vector-like objects, two-dimensional vectors I have written there, which could stand for the state of the spin of the particle or the angular momentum of the particle, or it could stand for the charge of the particle. The 0, 1 could mean that it's a negatively charged particle. Now, the point is that very often you don't bother to write all of this when you write down a quantum state, because you don't really care about all this information. Like if you are for example, if you go back to a 12th standard and you're solving your projectile motion problem, I am sure most of you did not bother about what color the projectile was, because color is probably not a quantity that you're interested in that context. You are probably more interested in trying to calculate its position and get the marks in your exam. That's about it. So in the same sense, a full description can contain many pieces, but very often you see the state vector represented as one of these pieces, not all of them, because that's a piece of information you are interested in. Okay. Now coming back, the statement that the state of a system is a associated with a vector in a vector space is a rather loaded statement. And the reason for that is that vector spaces have this uh, funky property that if you have got two vectors, if you know two vectors in that vector space, then combinations of those vectors, sums, differences, and sum of one with a multiple of the other, all those other vectors are also elements of the same vector space. Okay. Now, if you turn this argument on its head, the statement is that if you know of two valid quantum states of a quantum system, then arbitrary combinations of those states are also possible states of the system, because that's what this axiom implies. Because the statement is that states are associated with vectors in a vector space. So if you reverse it, you should have a state corresponding to a physical state of being of that system that corresponds to any arbitrary vector that you can construct from that in that vector space. So that reverse consequence is what is usually referred to as quantum superposition. Okay, by the way, I just put the dynamics. Yeah, I should have put probably Schrodinger's picture there along with like analogous to Newton's picture earlier. So this is the equation that talks about the dynamics of the quantum system. So, okay, so what does this superposition, the idea that convex combinations are also vectors in the same vector space, where does it logically lead to? So imagine this red dot at location x1 as the state of a particle which is located at x1. So that's a statement that is classically acceptable to you. You are finding a particle, it is located at x1. I put a little bigger blob to indicate that maybe x1 exactly you cannot find its location. It's there is a certain uncertainty window around it, but that's all kind of besides the point. Um, and another possible state of the particle is that it's at x2. That's also a statement that is quite acceptable in English to anybody, because you can accept that a particle can be at another location x2. But this principle of superposition tells you that there exists another vector and consequently another state of the system in which the particle is neither at x1 nor at x2, but it's actually at both x1 and x2 at the same time, a superposition of these two known states. Because once you find two vectors, you can add them, and those are also vectors, right? So if one can identify any two known states, then combinations of these states are also allowed. So in general, if phi and chi are two states of the quantum system, a superposition of this kind is allowed for a quantum system. So let us now consider a very simple quantum system. I am not worried about where that particle is located or what its charge is and so on. It just has two states, two possible quantum states it can be in. For example, it could be an atom with a restriction that it can be either in its ground state or in its first excited state. Or if you know a little bit about quantum spin, you will recognize that it could also be the these labels on and off or 0 and 1 that I have written could also correspond to spin up and spin down states of a spin half particle and various combinations like that. Or it could be 0 and 1 could correspond to left and right polarized photons, right? So it has two different states, and remaining aspects of that quantum systems, its location, etc., I don't care about, so I don't talk about it. And I label those states as 0 and 1. Okay. So then you can ask the question, how many states does the two-state system have? That sounds like a weird question because we just called it a two-state system. But then the answer, of course, is that, right. So let's guy the question, are you happy or are you sad? Okay, usually when you ask a question like this, are you happy or sad, you will elicit a response that probably says that the person is either happy or sad. A binary answer may be elicited, right? So I just put this in there to bring up something else. But let's come back to your two-state system. So if you, how many states does it have? In principle, it has an infinite number of possible states, because any superposition of 0 and 1 state of the form A0 plus B1, with the condition that A square plus modulus of A square plus modulus of B square equal to 1, is an allowed state of the system. So one convenient way of making sure that modulus A square and modulus B square sum to 1 is to parameterize it in terms of two angles, theta and phi. You can check that these two coefficients will, mod square will always add to 1. So, so the answer, the first answer is that, yeah, the two-state quantum system has an infinite family of states available to it, right? So in what sense is it a two-state system? It's in the sense of the binary response that could be obtained from the person who is neither happy nor sad. It is in the sense that if you ask the system, are you in state 0 or 1, then it turns out um, with probability P0, which is proportional to cos square theta, or probability P1, which is proportional, which is equal to sine square theta, the system will answer that I'm in state 0 or I'm in state 1, like the guy saying that I'm either happy or sad. Of course, being human beings, they could answer more in a more elaborate manner, but let's assume that way, just for the analogy's sake. So, so what is happening here? So what I'm talking about here is another idea that comes into picture when you talk about quantum mechanics, which is the notion of collapse of a wave function or collapse of the state. So as an additional axiom to quantum mechanics, one has to introduce this idea that when you ask a quantum system a direct question like this, or if you measure a quantum system and ask whether are you in state 0 or 1, it will actually answer I'm in state 0 or 1 with these probabilities, rather than actually telling you that no, I am this in this state psi, which is a superposition of 0 and 1. So that answer you will not get if you ask a direct question like this. Whether you are in state 0 or 1. And it doesn't stop there. And this is again something a little bit subtle, but very important for quantum mechanics. If you measure it, do a different measurement and ask, are you in the state plus or are you in the state minus, defined in this way, plus and minus themselves are superpositions of 0 and 1, then it will give a different answer, and it will answer I am plus or I am minus with a certain different probability which can be computed. Okay. Now, this process of collapse is a big question in quantum mechanics that a lot of people have been working very much on, especially in terms of foundations. Whether it is actually a quantum mechanical process, it's outside quantum mechanics, or is it just your state of knowledge? Is it ascribed to the system itself? A lot of interesting discussions are there, which I'm not going into. Okay, so we have really covered two different things. One is about quantum superposition, the fact that quantum systems can be in superposition, and then secondly, if you actually measure it, it will collapse with a certain probability. Now, one of the things that is believed to be true about this collapse is that this process is perfectly non-deterministic, in the sense that there is no way that you can predict what exactly the each measurement result would be. You can tell what probability you will get for 0 or 1, but in a particular measurement, whether it will jump to 0 or 1 is not something that you can predict. You can only tell the probabilities. Right. So this is another pictorial way of talking about the collapse of the wave function. In this case, we are talking about the position space part, a part of the state or description of the state. I'm interested in where the particle is. So the particle could be delocalized in a spread out wave function initially, but if I look for the particle, the wave function will collapse into a into a single location, telling me that as a result of the measurement, that the particle is in a particular place or somewhere else, whatever it is. It will give you an answer saying that I'm here or there, which it is expected to do, because otherwise that means that you cannot measure its position, which you can. So if you measure the position, it will give a definite answer, even though prior to that it was kind of everywhere. Right. So coming back to your quantum telephone, this what in very hand wavy terms, what is quantum about the quantum telephone is the fact that it has in it a random number generator, which they claim is uh, it produces a sequence of random numbers, which is truly random as guaranteed by the postulates of quantum mechanics. And that stems from another result that almost all other algorithms for, or rather, all other algorithms for classical algorithms for producing truly random sequences never really produce truly random sequences, but rather they produce what are called pseudo-random sequences. And the security of communication is tied to the randomness of the sequence that is being generated in ways which I don't have time to explain. But the point here is that, roughly speaking, what is happening is that inside there is a device that prepares and measures quantum systems. It prepares a quantum system in an equal superposition of 0 and 1, where 0 and 1 could be polarization states of a photon, electron, doesn't matter what the technology is. Then it measures whether that guy is in state 0 or 1, right? So it collapses to state 0 or 1 with probability exactly half, because I have chosen this particular state plus. The coefficients are both 1 by root 2, so mod square of 1 by root 2 is half. And the results of each measurement, whether it is 0 or 1, is recorded, and as a result of, and that sequence gives you a is believed to give you a truly random sequence. So that's a sense in which you are putting this quantum technology of random number generation inside a smartphone. Of course, right. I would be, of course, I don't know exactly what is happening, what system they are using inside that particular model, but this is roughly how it works. Right. So, right. So maybe I can pause at this stage before talking about more people and see if there are any quick questions that we can answer.
Yeah, Anil, Ashutosh Sharma, he asked the question, sir, does ket vector also have direction? If yes, then what does its direction signify?
Okay, that is I guess, a slightly a question without a direct answer, because these vectors are actually vectors in a complex vector space. So see, when you write a normal three-dimensional vectors, you can tell its components x, y, z, its projections on the x, y, and z directions, and those are all real numbers. But in a complex vector space, these projections are complex numbers. That's one. So, and secondly, it is not a three-dimensional vector space. It is a arbitrary dimensional vector space depending on the dimensionality of the system. So in the case of a two-level system, it's actually a two-dimensional complex vector space. So in that sense, a notion of direction in the conventional sense does not apply here. But as with any vector space, you can um, uh, define a notion of a direction. And in fact, in that sense, it's a good question, because it's really only that direction that matters. The length of the vector actually does not matter. So the true statement is that the states of quantum systems are associated with not really with vectors in this complex Hilbert space, but rather rays, which are such that two vectors with the same quote unquote direction but different lengths are thought to be or considered to be part of the same ray. So in that sense, it's a direction is the only thing that's important, but direction definitely is not direction as you conventionally understand
Yeah.
it. Okay.
So one more question is by Kevin. He says, sir, what is the advantage provided by the quantum technology in that smartphone?
Well, as you can see in the advertisement, what it says that it's secured by Swiss Quantum. So that comes through two different steps. One is that it is based on the understanding that having access to a truly random sequence of zeros and ones provides enhancement in the security with respect to the communication, presumably that the smartphone has with the cell phone tower or whatever it is. So that is a different set of mathematics, which I don't have time to explain there. And the point here is that the quantum measurement of a equal superposition state is believed to produce a truly random result. Okay, so it's about the true randomness that is involved, where that is touted as the advantage given by the quantum mechanics to this particular case.
So another quick question, sir. Uh, in the representation for 0 and 1 with cos theta e to the power phi and sin theta, what is the relevance of the exponential?
Oh, that is again, I guess, tied to the first question. Right. So there are different things you should appreciate about it. One is that, as I said, the coefficients are, this is a complex vector space. So if you break it up into components, then the coefficients are in general complex. So that e raised to I phi kind of underlines that fact, and it reduces that the possibility of having complex coefficient there. So that's in the mathematical sense. But that e raised to I phi, that phase, relative phase between the two, between the 0 and 1, it turns out is a very important character or component in the rest of the story. So that we will come to at least touch upon a little bit as we go along. Okay.
Yeah, I think that's also for the question.
Yeah,
Yeah, you can.
thanks, Manik. So let me go on and let's see how far we can cover in the allocated time. So let's complicate our problem further. Instead of asking one single gentleman or a lady about whether he or she is happy or sad, let's now put two people in the mix. Okay. Now, if you've got two people in the mix, classically there are four possible states that are allowed. Okay, there is a happy situation, which is everybody is happy, which is a nice one. Then there is the sad, happy, sad, and both are sad kind of scenarios, right? Well, that's well understood, right? But then in quantum mechanics, if you consider the state of both the people together, then possibilities like this start to appear, because happy is a state that that is acceptable to everybody. Sad is also a state that is acceptable to everybody, and it's known to exist. But then again, quantum mechanics tells you that a superposition of these two possibilities is also a possible valid state of this two particles or two bodies, right? So you can think of states that looks like this: a superposition of happy with sad. As such, it doesn't look too bad unless you think too hard about it, right? Because all I have said is that, okay, instead of talking about one object, I'm now talking about two objects and its valid states as well as its superposition state. So it's just quantum superposition applied to two bodies instead of one. But of course, people will think hard about it. And for instance, Einstein was very much discomforted by the possibility of such states. Not just Einstein, a lot of other people also. Because what it implied, so you can think through and you say, suppose one of the fellows is in India, say in Chennai, and the other fellow is in Paris, far away. And together they are in this state of happy plus sad. Now, if you go and look at the fellow, say in Paris, and find that that person is happy, as in the top case, then that necessarily means that the state of this two body system has collapsed into one in which the fellow in Paris is happy. But then that state is associated with the fellow in Chennai being also happy. So how does asking a question to the fellow in Paris suddenly determine the state of happiness or sadness of the fellow in Chennai? Does that violate the Einstein's idea of causality, or does it allow for faster than light communication? All these kind of questions started bothering people. And this, of course, is the crux of what a lot of people have thought about, and a lot of people confuse themselves about with respect to the notion of quantum entanglement. So this is the notion of quantum entanglement. There is a non-classical or non-classically understandable kind of correlation that exists between the two objects when they are together in a state that looks like happy plus sad. Okay, so that's called an entangled state. So that's another idea. Let's not dwell too much on its philosophical and conceptual implications, because that's an unending discussion, let's just uh, be let's just accept, like the what I said with the elephant, remembering what I said about the elephant, let's just accept that these kind of states are possible, and these are called entangled states of a of a pair of quantum systems, right? In one sense, it's just superposition applied to two objects. But if you think too hard about it, you will start finding that, okay, this could lead to some conceptual problems. Whether those conceptual problems are because you are a blind person looking at the elephant or not is something that you have to decide, right? So it can collapse into either one of these two states instantly. All right. Since I mentioned Einstein, I thought since we are talking about quantum technologies, this is a nice interlude to put in this picture of the Solvay conference in 27, which, if you have not seen, kind of contains in it all the heroes of quantum mechanics, the ones who essentially gave shape and flesh and form to quantum mechanics in its original form. And I titled my talk "The Second Quantum Revolution" partly because the quantum mechanics that were set up or understood by these gentlemen long time back, and I guess there are a few women, probably not enough. At least one is there, Madam Curie, right there in the front. But these people at that time, hopefully nowadays, these kind of pictures will have an equal representation. We're probably getting that. But anyway, so that being said, uh, the quantum revolution, the first one that they set off in motion, allowed us to understand a lot of uh, about how things work, right? About how transistors work, how MRIs work, or how build quantum clocks, build lasers, how semiconductor devices work, and so on. But the second quantum revolution, in a sense, started or set off when people started doing two things. One is tying the notion of information with quantum mechanics, and the second is trying to control individual quantum systems. Rather than understanding what is happening in terms of quantum mechanics, you are directly trying to manipulate the quantum world. So the tools and the technology and the engineering required for that had to develop over several years before you could handle that. And it grew, that capacity grew sort of symbiotically with the idea of combining the notion of information processing with quantum mechanics. So the notion combine that's the idea of quantum information theory, or quantum computing, as we will see later on also, which kind of gave partly the real fire and motivation to try and reach down to the quantum level and start controlling individual quantum systems. Of course, there are other motivations also, but this is one of the stronger motivations for doing the same. Right. So let me now sort of change track briefly in this talk, and talk about applications of quantum mechanics. Okay. One of them, in the context of information, stems from the idea that information always requires a physical representation, right? What I mean by that is that if I want to communicate or hold some information, I have to give it a physical form. It could be in the form of the sound waves that are coming out of my mouth, which are picked up by the microphone in my laptop and converted into digital signals, states of transistors, which in turn are communicated to all of you through states of light in an optical fiber, and it in turn is then converted back into sound by your devices, whatever you are holding. But at every stage, the information that is hopefully flowing from me to you or the other way uh, um, requires a physical representation. So if you extend that idea, then it also means that the ways in which you can transform and manipulate information, therefore, has to be controlled by the laws of physics themselves, because you cannot imagine a manipulation of information or change of the state of the object that is holding the information in a way that violates the laws of physics, because that's not allowed. Therefore, you are constrained in what you can do with in terms of of information manipulation by the laws of physics. So then you immediately are led to two different paradigms. A paradigm in which the dynamics of the entities that are holding the information are controlled by classical physics, as opposed to the case where the dynamics is controlled or it is governed by the laws of quantum physics. And as we have seen in the previous half an hour, there are key differences in the ways in which you can actually manipulate uh, quantum systems as opposed to classical systems. And as a result, if you hold information in quantum systems, there are ways in which you can, people realize that there must be ways in which you can manipulate information such that it is not allowed by if you were holding the same information on classical systems. So therein lies the origins of the idea of quantum information theory and quantum computing. Okay, so right, so that and I just put this picture here of a recent experimental result, which again tests this idea about of Rolf Landauer in 1961, who kind of summarized all this what I was trying to say by this phrase "information is physical." Because I'm not going into details of what this experiment is because we have uh, uh, a limited amount of time. But the key part here, or one of the key insights here, is that while classically information has to lie on, say, one transistor or the other transistor, or one pencil mark or another pencil mark, right? Quantum mechanics allows information to be delocalized across multiple physical systems. And that's precisely what happened in the happy, happy, sad, sad entangled state, right? You know the state of the entire system. The entire two-party system is in the happy, happy plus sad, sad state. So you know that. That's what state it is in. Whether you understand what it means, that's a different question, right? But by asking one of the individuals, you cannot tell what the state is. Because if you ask one of the individuals, he will either say happy or sad. It does not reveal information about the global state of the system, which is happy, happy plus sad, sad. So in a sense, the information about the state of happiness or sadness of those two individuals is actually lying across the two of them and not with any one of them. Okay, that's a little bit of a strange concept, but that's precisely what quantum mechanics tells you. Okay, so if you can place information neither here nor there, right, then you should be able to manipulate it also in ways that are different from what is allowed from by classical physics, right? So these ideas that we talked about in the beginning of the talk, quantum superposition, quantum entanglement, and much more general class of non-classical correlations in quantum systems, these are now seen as quantum resources, right? Which you can utilize to do what? You can utilize it to do different types of computing or addressing certain problems that are not efficiently addressable using classical computing. So that's the area of quantum computing. You can do communication also in ways that you cannot do with analogous classical systems. So that's the whole subfield of quantum communication technologies. You can do you can do measurements with precisions far exceeding what can be done using systems that obey the laws of classical physics. And that leads to quantum sensing and quantum measurement and various other things. Right? So it is the realization that all this is possible and the effort to actually put some of these into practice that is really now considered as the second quantum revolution. Okay. And these are some fancy pictures. People are now even selling quantum computers if you want. Now, I don't have too much time to talk about exactly how it works, but these are pretty pictures of the IBM Q System 1, which actually you can buy provided you have sufficient amount of money, but that's quite of a lot. But just heuristically, I would say this. Uh, if you take this very toy model or very crude assumption about computation, as abstractly as a device that takes an input and gives an answer corresponding to that input, which is the output. And suppose you want a right answer, and you will recognize it when you see it. So now this is a most computer scientists will probably shoot me for saying such things, but this is a very uh, crude way of putting it. But to illustrate, I'm saying this to illustrate the point that um, your inputs are say binary strings, like in the top left image, 00101 is your input and some output comes out. Now you can put 10111, some other output comes out. Now corresponding to some one of these input comes out, gives an output which we think, which is something we want, and we call it the right answer. Because of quantum superposition, what you can do is that if you replace the bits that are going in with quantum bits, which are nothing but the familiar two-level quantum systems that we talked about, then what it allows you is to put into the computer a massive superposition that contains all possible strings of zeros and ones in superposition, right? I have written the each of the input lines into the bottom figure as 1 by root 2 0 plus 1. If you take a combination of all of it, then it contains 0, 0, 0, 0, 0, it contains 1, 1, 1, 1, 1, it contains 0, 1, 0, 0, 0, and everything in between. So all possible inputs are going in one shot into the computer and does something, and out comes an output which probably is a superposition of all possible outputs. But it turns out there are some clever ways of sort of pulling out the answer that we want to get. A sort of massive quantum parallelism is what I want to emphasize by saying all this. Now, getting the right answer out of the output is a really clever bit, and that is the interesting and exciting field of developing new quantum algorithms, right? So you kind of have to think quantum mechanically in order to figure out ways of getting that answer that you're looking for out, or to design a new quantum algorithms, right? So, and that is indeed a challenge, because we are, after all, classical beings. This is just trying to say what some of the talks earlier were on chemistry, right? And also paying homage to the original idea of a quantum computer as proposed by Richard Feynman, who said that in general, simulating a quantum system like a large molecule on a classical computer is an extremely hard thing, right? So he asked the question, why not use another controllable quantum system to do the simulation for you? So the difference is the other one is a molecule that's just given to you or you think up. The other side, you have a controllable quantum system made out of elementary units which you know how to initialize and control and manipulate. Why not simulate a, 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 a large molecule using a quantum computing device or doing a quantum simulation? And this is another exciting frontier that's coming up quite fast. This is a result from the Google in 2020, where they used their quantum computer to simulate uh, certain molecules, certain properties of certain molecules uh, um, at speeds which are totally unheard of when it comes to using classical computers to simulate these molecules of the same size. Anybody who does real quantum chemistry on a classical computer knows how long it takes to actually find the relevant things about a large molecule in a classical computer, right? So that's another interesting frontier. And this is that Google's quantum computer. It kind of looks like the IBM's one, except the box is red. Rest looks the same. Sort of looks the same. But they had this interesting result in 2019, where they claim to have, or probably is accepted to have done, a problem which would otherwise take the best classical supercomputer that we have at least 10,000 years to compute. Okay, there has been some debate on whether that's really true or not, but it's roughly there. Okay, and what that problem is, actually it's kind of a useless problem to solve anyway, but they just wanted to show that they can solve one problem which otherwise would take forever on a classical computer. Uh, uh, and what goes into building a quantum computer, that's also quite exciting because there is a lot of quantum physics. There's a lot of knowledge of materials, chemistry, about cryogenics, about electronics. You also need experts in computer science, theoretical computer science, new mathematics, and of course, there is nowadays a lot of economic interest also in terms of funding in trying to build some of these devices. And there are many promising approaches to building a quantum computer because in the end, all you need is a collection of two-level quantum systems that you can control. And those two-level quantum systems could be trapped ions, it could be cold atoms, it could be spin of electrons in semiconductors, it could be photons. And one of the leaders of the pack is superconducting qubits. The two frames on the right side, this picture is taken from a old workshop that's like 3 years old now, where they talk about the promising approaches to building a quantum computer. At that time, supercomputing qubits were circuits were leading, but nowadays trapped ions are making a strong comeback by this announcements by this company called Honeywell, who is building a trapped ion-based quantum computer. Right. There are other, as I said, communication is another area. There is a whole area of doing quantum secured communications or quantum key distribution. And China, a few years back, demonstrated satellite-based quantum cryptography or quantum key distribution, to be more precise, which kind of slightly spooked a lot of people around because the communication is secured by the laws of quantum mechanics. And to the extent quantum mechanics is true, it can be shown that with some caveats that it is in principle unbreakable security. Therefore, that is something that is strategically important to various countries, and there's kind of a race to get this going on a global scale by various countries. And even in quantum communication, there are challenges because uh, um, transferring quantum information from one form to the other. If quantum information is sitting in superconducting qubits, you want to transfer it onto photons so that you can send it somewhere, right? When you send it somewhere, you need repeaters so that you can send it far. So there is a lot of quantum optics, traditional optics, photonics on a chip, all coming in here, which is another exciting frontier. And finally, of course, the goal would be something like a quantum internet, whatever that means. This is a caricature of doing measurements precisely using the quantum resources also. So I will not, probably in the interest of time, I will not go through this in detail. But the idea is that you have, say, a magnetic field of strength phi that you want to measure. And what you do is that conventionally you will send some particles, some n particles, which I, for the moment, call the quantum probe. You kind of send it through this area with the field, and something happens to them. They come out in a slightly different state. And by looking at what state it is in, or what changed in them, you will be able to kind of estimate this magnetic field. This is or could be a temperature field. So all these little green dots you think of as thermometers that you send in through the area with the temperature you want to measure, and it has changed its state. The temperature reading has now changed. I guess many of us don't remember, at least the students may not even remember mercury thermometers, but anyway, it doesn't matter. Digital thermometers work just as fine. So what you have done is that you've done a bunch of measurements of the same thing, and when you do many measurements, as you may have learned in your physics lab somewhere, that you will get a better estimate of the parameter. But quantum mechanics allows you to do some more fancy things. Rather than sending these particles one by one and using them to estimate phi, you can combine them together into esoteric quantum states. I have called this the Schrodinger cat state for a particular reason, but I will not go into that. And you can use these quantum states, which are actually entangled, and send it through this field, and something happens to the cat. And by doing the appropriate measurement, it can be shown that you can get a much more precise estimate of phi than as opposed to doing the measurement using independent systems. So you use the quantum resource, in this case entanglement, for doing something in a much better way. Okay, and it has I guess this I will probably skip. The same idea comes out in a totally different form, and it is being applied now in the LIGO gravitational wave interferometer, where quantum states of lights is used to improve the precision in the detection. Okay, so the current run of LIGO uses an idea sort of introduced back in the 80s of using squeezed light to improve the measurement precision, because the gravitational wave detection requires such extreme precision that any small advantage or small improvement helps. So quantum technology, in a sense, is applied in sensing and measurement presently in LIGO gravitational wave detectors. This is just a flyer for the national mission on quantum technologies, which is supposed to be launched soon, so that there is a strong initiative in India to join the race of developing quantum technologies and applying quantum mechanics to day-to-day life, as I had uh, mentioned in the beginning. So thank you for your attention. Manik, I hope I have not overstepped my bounds as
Yes,
far as time
yes, we
goes.
have actually a few minutes to take some question.
Right.
Yeah.
So, yeah.
So if anybody, so Rohit Menon, he asked some question. Sir, what you had mentioned about superposition put into a quantum computation.
Mm.
Okay. Sir, when you had mentioned about superposition put into a quantum computation, is this computation a more analog setup? That is, where we have to manually set up the system to solve problem, or can it be programmable like the computers we have today?
Well, I guess the answer is that what one is going towards is a fully programmable quantum computing system, right? We don't want it to be custom set up for every case, but we are still in its infancy. So imagine the old vacuum tube based classical computers that filled a huge room. One is kind of in that stage now with respect to, or maybe slightly more than that stage, when it comes to actually having a quantum computer. So number of units that you have, or quantum bits that you have, the record is now at 50, 60, that number only, as compared to the number of transistors that are there in your laptop, which runs into the billions, right? So things are still at elementary stages, but definitely the aim, the objective and the idea is to build a fully programmable quantum computer. Otherwise, custom built ones are not very used or very much used. But I should also
So,
mention that in the context of simulating quantum systems, right now we do try to do custom built ones also, because even then it's still kind of that advantage is quite useful.
okay. So Venkatesh Jha asked one question. Sir, a slightly off-topic question. There are instances of migratory birds employing quantum effect to find roots, and bacteria using quantum tunneling and vibronic mixing to channelizing energy, which are addressed in domain of biophysics. Sir, is there any some sub-branch of quantum computing which takes result of these biophysical studies and utilize them to enhance our own quantum technologies, supercomputer, quantum satellite, etc.? If not, is there possibility of such branch emerging in near future?
Right. So that's a great question, because indeed there is a, I wouldn't say realization, but there is a uh, nagging suspicion that evolution and nature may have figured out means of controlling quantumness or preserving quantumness of certain systems for much longer and much more efficiently than anything that we know of. Okay, so one of those examples, as you said, there is a belief that avian magnetoreception is essentially a process mediated by quantum coherence. Okay, or more importantly, it's a process mediated by preserving quantum coherence for long enough times that uh, 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 a chemical mechanism which follows essentially um, gives the bird a way of sensing the direction of the Earth's magnetic field. So when it all works out, literally what we believe is that the brightness of the sky that a bird sees, a migratory bird sees, could be modulated by the direction of the magnetic field of the Earth. So in the direction, the north-south direction, it may end up seeing a darker sky than in the away from the north-south direction. So literally, there is like a compass in its field of vision. But again, for this to work, you got some way of, we need some way of sensing a magnetic field by which is by all measures is very, very tiny. Okay, and that mechanism, the one of the understanding is that it requires certain coherences, quantum coherences or quantum superpositions in molecules to stay for a long time, or rather stay for a length of time which we don't know how it could possibly stay that long, right? So maybe nature and evolution has figured out a way of preserving this superposition for long enough for such an effect to give migratory birds a means of finding the north-south direction. Okay, so that's so yeah. So a different part of the answer to your question is that uh, if you want to understand whether there are quantum effects in large molecules like the ones that participate in photosynthesis, then simulating or computing the properties of such large molecules fully in a classical computers is way beyond what is imaginable or possible, because these are very large molecules.
Yeah.
So the idea of quantum simulation that I talked about comes into play, wherein you can use potentially a future quantum computer to simulate these molecules and understand the processes that happen and see if photosynthesis employs quantum coherence and entanglement, superposition to do a very efficient capture of light energy, solar light energy. And if you can do that, then we can actually utilize that to our advantage to building better light capturing devices and so on.
So Omkar raised his hand. Omkar, can you ask your question?
Yes, sir. Hello, sir. I had a question related to quantum entanglement.
Mhm.
So basically, when we say that two particles, let's consider two particles are entangled with each other. And sir, first question is like, does the distance matter between them? Like for entanglement, is there a specific distance that
No,
should matter?
no, as far as the postulates of quantum mechanics goes, the distance never even comes into the picture, right? So distance has no real effect. Now, how to separate out the two particles and why you separate out the environment destroys the entanglement, all that are, I guess, other questions. But in principle, the distance has nothing to do with it.
Okay, sir. So actually, I wanted to ask is if they are kept at a considerable distance, let's say 2 or 3 kilometers, and supposedly we observe one of the particles, so that its wave function collapses and it gets into one quantum state. So how does the other particle also know that it has to get into the same quantum state as the first one has collapsed?
Right. So now that is the sort of the million-dollar question, right? How did it know? Now, but that's what the quantum collapse postulate tells you. Now, there is a mitigating factor there in the sense that one can prove that you cannot use this phenomena to actually transmit any information faster than light. That's called the no signaling theorem, and explaining it is a little subtle. While this collapse may happen, let it happen, but you cannot use it to actually communicate something faster than light. That's a different aspect, right? So in that way, Einstein's notion of causality is still preserved, right? But if you ask, how did it know, or did it know, or was it always in that state? Those are questions for which currently there are no clear answers.
Okay, sir. Got it. Thank you, sir.
So one more question Kevin asked, Sir, I have heard of slowing light to walking speed of humans. Is it possible? If yes, how?
Right. So that is possible, right? And that actually, as well, you use some interesting quantum mechanics to do that, but understanding that probably does not always require quantum mechanics to do it. It is a question of really what is called the difference between the phase velocity and the group velocity of light. A packet of light, as opposed to the components or the waves that make that packet of light, the way they move can be modulated relative to each other, so that you can actually slow down light, right? So in a sense, even if when you pass, you know that when you pass light through a glass slab also, uh, its effective velocity there is changed, right? And you can push it to extreme, and you need some interesting quantum effects to do that. And that's when you get this extreme slow light, holding light, and so on and so forth. But uh, yeah, so indeed that is possible. That's, I guess, the short answer to your question.
Any more question? Anyone has any more question? Joy.
Okay.
Yeah, anybody has any more question? Okay, if not, let us thank the speakers once more. Thanks, Anil, for explaining this promise of this second quantum revolution. I hope student has get some idea, okay, what this second quantum revolution promises.